Good evening, everyone. Uh, Welcome to today's section on problem solving week 8 IIR filter implementation. First, let us we will discuss the signed multiplier architecture. I consider signed two's complement fixed point representation. So A is equal to A3, A2, A1, A0, and B is equal to B3, B2, B1, B0. Then if I consider Y to be only 4 bits, then I will be excluding the LSB bits. So this will be Y3, Y2, Y1, Y0. So the decimal representation, now A will be minus A3 plus A2 2 to the power minus 1 plus A3 2 to the power minus 2 plus A0 2 to the power minus 3. B is equal to minus B3 plus B2 2 to the power minus 1 plus B1 2 to the power minus 2 plus B0 2 to the power minus 3. Then Y will be, I am multiplying every term of B with the complete A, minus B3 plus B2 2 to the power minus 1 plus B1 2 to the power minus 2 plus B0 2 to the power minus 3. This is A minus A B3 plus A B2 2 to the power minus 1 plus A B1 2 to the power minus 2 plus A B0 2 to the power minus 3. So now I will write it in a little different way so that we can directly use it to implement in the algorithm. A and B terms I am writing separately, and then now I will write the 2 to the power minus 1 terms. So with A B0 I have 3 times. So 1 time 2 to the power minus 1, second time 2 to the power minus 1, third time 2 to the power minus 1. So you can see A B0 will have 3 times multiplied with 2 to the power minus 1. A B1 will be multiplied 2 times. A B2 will be multiplied only once. So now this Y we can use it, and then we will implement the algorithm. First let us write the algorithm. So Y is minus A B3, and write the same Y plus A B2 plus A B1 plus A B0 2 to the power minus 1, 2 to the power minus 1, and 2 to the power minus 1, 3 times. Now, if I want to implement this, then A3, A2, A1 is 0, multiplied with B3, B2, B1, B0. First will be A0, B0, A1, B1, A1, B0, A2, B0, A3, B0. The next term will be A0, B1, A1, B1, A2, B2, this is 1, A3, B1. Now, this term I have to perform sign extension, so I will have A3, B0. This is called as sign extension. And if I am performing A, B0, 2 to the power minus 1, it is one time shift, so this will be removed. Then I will have PP0, partial product 0 for the 0 term, partial product 1, partial product 2, partial product 3. Now if I multiply B2 with A, so A0 B2, A1 B2, A2 B2, A3 B2. Now here again I have to perform the sign extension PP partial product 3. Now at this stage, this will be removed if I am using only the 4-bit representation. When I am performing 2 inverse 2 times shift. And then this one P partial product 0 2 partial product 0 this first partial product, second partial product, third partial product. Now B3, so A0 B3, A1 B3, A2 B3, A3 B3. And this one again, this term will be removed if I am performing A B1 plus A B0 2 in one time, second time, and then now I have with A 2 inverse. Again here there will be sign extension. So you will get Y3, Y2, Y1, Y0. So this will be the result and in 4-bit. I'll make one more step. Now if I implement the architecture, let us consider one small module like this is the called as processing element. Here the considered processing element is giving the output S out plus C out, which is S in plus C in plus A input B input. This is nothing but one AND gate plus ladder. It has the input S in, A in, B in. So this B in will be propagated here. And carry input, carry output, and then this one. This A out will be A in. A will be propagated and B will also be propagated, and this will be the AND with one ladder operation. So now this signed multiplier is the same architecture I want to implement. So 4 cross 4, there will be total 16 such processing element. So this architecture is also called as systolic array architecture. Here you cannot, like, each processing element will not be accessible, but the A in and B in will be propagated. Like A0 from here, A0, B0, A3, A2, A1, B1, B2, B3. Now all this processing element will receive B in, which is B0. Let this be first, second, third, fourth question element. So this also B0, B0, B0. And all this will be receiving A0. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16%. So this one will also receive the one. This one. Now this um, this A1 here also next is SM for the first carry input CM is equal to 0. The next stage this carry will be propagated. And here you can compare CR. Then we for this S input I have to right. This I will get the A3 B0 SMS 0 and CNS also 0. So in that way this will be the output. Here A to B0. This one A1 B0. This one into the product. This will be giving A0 B0. Now like if I take the first processing element S out plus C out is S in C in plus the A input B input and operation. So here this is 0, so I will be getting A0 B0 only one term. So carry will be 0. Again the same way for this complete row carry will be 0. Next here we have to perform the sign extension, which is nothing but this term A3 B2. So this will be my sign extension. And then same way this output will be this one. P3 is 1. Okay, here also we will have C in which is 0. And this carry we will propagate it. The same way from here and from here. This is the second layer. This output will be Y0, Y1, Y2, Y3. Again same way there will be carry propagation. And this time carry it should be B3. And in the last layer we needed minus sign, so it is complement. We will add it here. Then this will be connected here, and again this also will have some 0, so 0. Then again for this I need a sign extension, so I will take it from here. And then again for this we need sign extension. I will take it from here. Yes. So this is the architecture for this algorithm. Next, Bahuli multiplier. This is a sign multiplier. So again, like same representation, if I consider A equal to A3, A2, A1, A0. So this is in the decimal representation minus A3 plus A2 plus A1 to the power minus 2 plus A0 to the power minus 3. Another number is B3, B2, B1 minus B3 plus B2 plus B1 to the power minus 2 plus B0 to the power minus 3. Multiple A equal to Y equal to minus A3 plus A1, A3, A0. A3 into B3 is the positive term. Get negative term whenever A3 is multiplied with all this term. Same way B3 is multiplied with all this terms. So we can write it separately. B2, B1, B0. This as well as B3 into same A for A terms. A2, A1 to the power minus 2 plus A0 to the power minus 3 plus the remaining terms plus A0 to the power minus 3 to the power minus 1 plus B1 minus 2 plus B0 to the power minus 3. This is power. Now minus A3 with these terms, B3 with these terms. Perform the final Let us consider minus A3 B2 2 to the power minus 1 B1 minus 2 B0 minus 3. My, this is minus is common, so plus. Now minus multiplying this with B2 plus this term and this term. B3 A2 2 minus 1. So A3 B1 B3 A1 A3 B0 plus B3 A0 now minus 3 minus for taking the complement plus 1 minus B3 with the complement because they are negative numbers. So there are 1 minus 3 4 minus 3. Terms means this is the decimal equivalent. Why we took A and B values like that, and are there any default or we can change the terms? This is the decimal equivalent representation of this fixed point notation. So I have directly taken this values A3 dot A2 A1 A0. So here I have 1 plus 1, so it is 2 into 2 power minus 1. So all are plus terms only. Again 2 into 2 power minus 3 plus A3 plus terms which are this term with minus 1 plus 1 by 2 plus 1 by 4, which is minus 7 by 4. So you can write as 2 minus 1 by 4. This is an overflow. So it is approximated as 1 by 4. This is 2 power minus 2. So I can add plus 1 to where the term is 2 to the power minus 1. This term I should add 1. So you can do it in the next step. A3 B2 B3 A3. So this you will see like for 4-bit B3 is the must be. So wherever B3 is multiplied with A0, A1, A2, that value will be complemented. B3 A1. Now 2 to the power minus 2. We have to add 1. And 3 B0 plus B3 A0. Now this final This y is, this is the previous, this positive number, and then this multiplication, the remaining positive multiplication. Minus 3, b2 to the power minus 1 plus b1 to the power minus 3 plus b0 to the power minus 3 plus this term, which is the negative term. So we have taken all the complements and then b1 plus b1 plus this one for 2 to the power minus 2 term, a3 b0 plus b3 a0 for minus 3. Then now if you multiply, then you will be getting all the terms like 3, 3, 2, so till minus 6, to the power minus 6. So a3 b3 plus a3 plus b3 b3 maybe you can see it. Plus the y term. So if we write like this algorithm, will be 2 to the power minus 6, minus 5, minus 4, minus 3, plus 1, a0 b0. So you can see only a0 b0 term is there. So a0 b0 is this. Then a1 b0, write this information. a2 4 a5 a6. This is a 4-bit multiplier. C0 to a3, a0 b1, a1 b1, a2 b1, a3 b1, a3. Then a0 b2, a1 b2, a3 a2 b2, a3 b2, a0 b3, a0 b a1 b3, a2 b3, a3 b3. So next for 2 to the power minus 5, it is a1 b0, a0 b1. a1 b0, a0 b1. So this is correct. Then next, this is 0. The next is a2 b0, a1 b1, a0 b2. For 2 to the power minus 4. a1 b1, a0 B2, then the other term A2 B0. This is the second product term. Next is this complete. So if you see, it is for 2 to the power minus 3, A3 B0, A2 B1, A1 B2, B3 A0. So this is also fine, P3. Next, for this three terms. This one, A3 B1, A2 B, and then A1 B3, and 1 is there. This one also we need to add this algorithm, and wherever 3 is there, those terms are complemented. Then this one is P4. This Brown multiplier present is in every ALU. Brown multiplier is unsigned multiplier, and this Bahuli multiplier is for signed number multiplication. ALU consists of multiplier unit, but which type of arithmetic, whether signed or unsigned, based on that the multiplier type will depend. Then next is 2 to the power minus 1. These are the terms. Let us check. It is A3 B2, A2 B3, and last is A3 B3. So P6 and then P5. So this is the algorithms. Now if this is the multiplier algorithm. So here it is direct. We need one AND gate. Here we need one half adder. This we may need one half adder. So it will have intermediate result W's, and this will be the product term. Then again this we can combine. We will have W2. Now this completely W1, W2 we can combine. This will be having output W1, W2, W3. This will have an output W say 6, because if we have considered this 2, then W5, and then this will have W4. So the same way you can combine with half adder plus full adder. So this Bahuli multiplier architecture requires 8 half adder plus 7 full adder. Optimum design. So now the same above algorithm, if I implement using the architecture, A0, B0 direct AND gate. So here we will be getting 8 bit result. The next half adder A1 B0 A0 B1. This sum T1. This carry W1. And then again I have to add it A0 B2. This is full adder. So here half adder. This sum can come here. This is W2. So this is A1 B0 A0 B2 and then another carry again a full adder. So one A1 B2, then here one carry which is W4 from this half adder. So A2 B1 A3 B0 then W5. So 1 2 3 4 5 and then this sum is product 2. In W6 full adder A0 B3 bar W7 full adder W8 A1 B3 W9 here another full adder W5 A2 B2 and then A3 B1 and then this is W9 and then full adder W10 and then A3 B2 bar and A2 B3 bar W14 W15 B3 B3 W13 W10 and here I need 1. This output is P3, this output is P4. Now next stage, W16, W17, this is also half order, W18, W19. This maybe we can remove it. This also, this will be W21, 19, 20, 21. This can apply to half order. This is P5, P6, P7. So this is the architecture. Now we will write the Verilog code for this. We will write all the instantiations around here. Preparing half adder, one. So first half adder is, you can see A1 B0 and A0 B1. So A1 and with B0, A0 and with B1. Output is PM1 and W1. The same with second full adder. Second, okay, let us say this half adder. A A2 B0 A1 B1. A2 B0 A1 B1. A1 2 1 W2 W3. Second half adder A2 B1 and then this complement. So complement of A3 and B0 and then A of 2 and then 0 1 W2 W1. The same way for full adders. A1 W1 W2 and then A0 B2. W2 W1 A0 and with B of 2. B of 2 W6. F ladder 2. So the same way you can write for the other full adder is half adder instantiation. So Verilog 4 we have module name and then inputs are 3-bit it's 4-bit 3 down to 0 4-bit A B and then the product term will be 8-bit so 7 down to 0 product and we need 1 1 6 and then wire from W1 till 23 wires. Let's see 21 22 23. So and then here half adder and then full adder instantiation. So we are instantiating this. These are not the inbuilt primitives. So we have to define half adder this xy sx here. So input x comma y, output x comma 0 assign S is equal to X, Y, C, assign C out X and Y on by three inputs. I think this is the C out. And then end module. The same way module full adder. X, Y, C, S, C out. Outputs are S and C out. Assign S is equal to X, Y, assign C out.
Hello, ma'am.
Yes.
Yes, ma'am. For this you said it required 8 half orders and 7 full orders. But in the diagram, I am seeing only 7 half orders and 8 full orders. Could you please clarify it, ma'am?
Said eight.
Sorry for the disturbance, ma'am.
No, no, no problem. I said eight half adder and seven full adder.
You said 8 half orders and 7 full orders. But in the diagram, it is available like
Okay, one second.
8. 7 half orders. In the diagram, only 7 half orders available.
2, 3, 8.
Yeah, 8 full orders is coming.
Okay.
And the correct answer is please.
For this design, I am getting
Yeah, 8 full orders and 7 half orders is coming.
yes,
But initially you said 8 half orders and 7 full orders.
yes. For this particular design, I am getting this. I don't know whether any other optimal
Yes,
design is
ma'am.
possible, but
Okay, ma'am.
yes, for me, in this design, we are getting yes, this requires three input.
The correct answer for that question. Yes, ma'am. For the correct answer for that question is 8 half orders, 7 full orders,
I
or
think here this is a half adder. This is a half adder. It is only two
7
inputs, right?
half orders, 8 full orders, ma'am. Please.
No, this F8, this particular block, it is, I have written full adder, I think by mistake. This is taking only two inputs, so this half adder is enough for this.
Eighth one. Eighth one. Yeah, yeah, yeah.
Yes, so eight half adders and seven full adders. Okay,
That
I
is
think
half
that's
order,
it.
no? Oh, okay, okay, okay. The eighth one,
Yes,
eighth.
yes, this full adder, which is having
Yes,
W13
yes,
and
yeah.
W13.
So the initially you said this correct. Yeah, yeah, yeah.
Yes, yes,
Very good, very good. Thank you, thank you very much, ma'am.
sorry for that. Yes, yes, welcome. Sorry for that. I have made like I have given only two inputs, so half adder is enough. Thank you for that. Sorry for this mistake.
Thank you, ma'am. Thank you, ma'am.
Yes, this is the Verilog code. The same instantiation you can like write for all the half adder and full adder, and the other, this will be the input and output port, and one will be required for this particular here full adder, and then the other code for half adder and full adder. So now we can implement the IIR filter, infinite impulse response filter. This we consider as the equation A y of n minus 1 previous output and x of n. So this we will have x of n, y of n. Delayed version of this will be y of n minus 1. This one multiplied with a, then added, we will get ay of n minus 1. So this multiplier we will use the Bahuli signed multiplier, then normal adder. So now if we write the Verilog code for this IIR filter implementation, module IIR filter block and reset A, X and Y. The inputs are block, reset, and then 4-bit input A comma X, and then the output 120 Y, H 3 down to 0 Y value, then multiplier output. So Bahuli multiplier, so Bahuli product term, and then instantiating the Bahuli multiplier, then this D flip flop. Always at the pause, exit, block, reset, X, reset, Y value is X, and then end. It will be only X, otherwise this complete, like this flip flop will be reset, so just X, otherwise else begin Y value will be X plus this Bahuli multiplier product. Straight on to then one end for else, another end for always block. Then we can assign this Y value to 1. And this will be the AR flip. So D flip flop implementation and D flip flop with add, and this is a multiply instantiation. Just to mention, I will AR the and then inputs will be registered in the test bench wire 3120 volts. Then we will call this IAR filter. Then instantiation name of this values. Initial begin means it will be executed once at t equal to 0, no time mention delay. Then always with the delay of 5 minutes, clock should be conserved. The next initial begin, then reset V1. We can apply somewhere is 40 D2. Again some delay, reset is equal to 0. A is equal to again 40 D2. So we will 40 0 right. So what is the IAR filter function? A into y of n minus 1 plus x of n. So for us A is 2 and then x is 1. So first at one particular instance of clock, 2 into previous input is 1 plus 1 3. The next instant A equal to 2 3 plus again 1 which is 7. So in this way it will be proceeding. At instant 0 this will be 0 because A is 2 plus x is 1, so 1. So 1 3 and then S will be proceed. Now let us try some previous year tools. For so the following is true for the Bahuli multiplier. 8 half adder and 7 full adders. 8 half adder plus 7 full adder. Option C. The next question. A is equal to decimal 99, B is decimal 88, and C is again decimal 77. We shows the execution of this dollar step. So we have not performed any other operation. So this statement is dollar display is used to display these values, and percentage with B, O or H represent which data type you are displaying. So this one here A will be mapped, here B, here C. So A will be displayed in binary format, B will be displayed in octal format, and C will be displayed in hexa format. So if you simulate this, So we only this is the code. So these are the values given in the question. So now if we simulate it, uh, I have given some length, just sufficiently more to store 99, which is the highest value. Maybe this many bits may not be required, but I'm just using it. So initial begin, they have given before execution A is 99, B is 88, and C is 77. Then I am displaying the percentage B A, percentage O B, percentage H C. So next, if you simulate it, you can see dollar display will display it in this here. So first is 110011 and 130 and 4D is the answer. So it is 110011 130 and 4D, which is option A. And third question, 2's complement representation of minus 16. Now to represent 16, this is a decimal value, base 10. To represent this in base 2 system, we have 8, 4, 2, 1. This will be 15. So I need one more with 16. 1, 0, 0, 0, 0. So 4 zeros 1. So they have given 8-bit representation. So in 8 bits, 1, 0, 0, 2, 3, 4. Okay. I am representing 8. 1, 2, 3, 4, 5, 6, 7, 8. This is plus 16. The ones complement for this is, then 2's complement will be plus 1. 0, 0. 1 plus 1 is 1, 0. Again 1 plus 1. 0, 1, 1 plus 1, 0, 1, 1 plus 1, 0, 1, 1, 1, 2, 3. So 4, 1, 4, 0. So minus 16 in 2's complement representation and 8-bit format is 1. So this is the plus 16 and which becomes for the 2's complement representation. Then next value, 4-bit fixed point normalized signed 2's complement representation of A is. So this is fixed point A, 3, A2, A1, A0. And okay, this is, I think the subscript is not missing here. A 2 to the power minus 2. Okay. So this is A into 2 to the power 0. A into 2 to the power minus 1 will be one time shifting. So A1, A2, A3 and A3. This we have seen the sign extension. So A 2 to the power minus 2 will be again one shift. So this is A3, 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 A2.
Ma'am, how A3 will repeat?
Yes, in the 2's complement, like for the sign representation, we have seen the sign extension. We were performing in the previous slide also. Yes, here when we were doing, we want to add it like 2 to the power minus 1. So we will drop till this one and then this bit we will assign extend. for signed numbers, this last MSB bit will be sign extended.
Okay, ma'am.
So in the same way, here also sign will be extended. If again if we will have to shift say 3, then this A2 will also be shifted. It will be only A3. So in the question they ask for A 2 to the power minus 2. So 2 times shifting is the right answer. So this is A 2 to the power minus 2. Then A is shifted 2-bit position to the right. Here for binary, if you want to multiply with any power of 2, if it is say 2 to the power plus 1, this is base 2 to the power plus 1, then you will be shifting to the left. Like say if it is 1 0, which is 2. Now 2 into 2 it is 4, which is 1 0 0. If you want to divide by 2, say 2 to the power minus 1, and it is 4, then you will have 2, which is 1 0, shifting to the right, and this is shifting to the left. This is for binary. Any doubts?
Ma'am, 2 plus 1 means left side shifting position. A3, A2, A1, A0. That times
No,
shift means.
I am just generally explaining. If like for example, if you want to multiply any binary number with 2 to the power plus 1, then one left shift is enough. Like, and if you want to multiply 2 to the power plus 2, then 2 times left shift you can do. Here in this representation, it is after dot. So it is like here 2 to the power 0, 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. So this is how we have initially multiplied. See here, this A3, A2 is 2 to the power minus 1, A2 is 2 to the power minus 1, A3 is 2 to the power minus 2, then minus 3. So here for our calculations, we require this minus sign. That's why we have only shown this one. But generally in a binary, if you want to multiply by 2 to the power plus number, you can shift left, and 2 to the power minus, you can shift right.
Okay, ma'am.
Any other doubts?
Ma'am, explain this by taking 4-bit binary number.
Like with value you are asking?
Yes, ma'am.
Yes.
By considering some value. Yes.
You can, if it is a negative number, so okay, let me take 0 0. If this is the value, then if this is a 2 to the power 0, then a 2 to the power minus 1 will be 1 0 0 0. A 2 to the power minus 2 will be 0. So this will be shifted here, this will be shifted here, and this will be shifted here, this will be shifted here, this will be the sign extension. This will be shifted here, this will be shifted here, this will be the sign extension. if it is 1.011, then a2 to the power 0 and a2 to the power minus 1 will be 1, this one, this 0, this one, and then sign extension 1. a2 to the power minus 2 will be this 0, this 1, this 1, and then this sign extension 1. Correct, right? Any doubts?
Shifting 4-bit position means?
Like a2 to the power minus 4.
Okay, ma'am. That number denoted.
Okay, number, if you shift it again, then this magnitude will be completely like lost. You will see only the sign bit getting repeated. Because it's like you have say 4, you are shifting it once, you will get 2. If you again shift, you will get 1. Again, if you shift, it is 0.5, which is 0. So if this is the number, again one shift, another shift will be 0. This is positive, so 0 will be the. So this is for binary. Any doubts? Clear, right?
Yes, ma'am.
Next question. Which of the statement is false? So in the previous class we have discussed the Brown multiplier, which is for the unsigned numbers, and now in this class we have discussed the Bahuli multiplier, which is for signed multiplier. So this statement is also true, and this statement is also true. So they have given which statement is false, so not the all of the above, not this and not this. So the conventional parallel multiplier hand is sign bit in an efficient manner. So this is the false statement. So option C, because Brown multiplier is used for unsigned numbers and Bahuli multiplier is used for sign multiplier. So the correct option is C. Now in the Verilog code, this is used in the test bench. So if you are using say a delay of 5 and then you display with $time, here you will see the output, it will display as 5. So $time is used to display the current simulation time. And this is a non-synthesizable code, and this is used in the test benches. Now,
What about hash monitor, madam?
dollar monitor.
Yes, madam. Yes.
Dollar monitor will also will be used for display. Time is for displaying the how to say the time of execution. Like if we are having say here, if we display, then this values it will be displaying as time 0. This values has time 10. Dollar display for the capturing the time variable, And for displaying the values, we will be using the dollar display and dollar monitor.
What is the main difference, madam? Display and monitor.
The display will be used inside the initial and begin block. Initial, like here, inside the initial, begin and end. So it will be like usually used to display some message like, okay, this is the term we are displaying. And so once it is executed, it will be like displayed. But dollar monitor will be displaying whenever there is a change in the value. So like here A, B, C are constant, so we have used dollar display and displayed it once. But dollar monitor, whenever there is a change, it will again display the value.
Okay, madam.
Here, I am here. So you can see it has displayed once. But again I have given some change after 2. That change is not captured. So you can see when I use monitor, both the values are displayed. My screen is visible, right? That simulator window,
Yes, ma'am.
you can see when I used dollar display, only this line was visible. But I have given a change after 2 unit of time. I have changed the D to 0. So when I'm using dollar monitor, both the change values are displayed. But now again, if I change it to, sorry, not here, here, DI, yes, P, L, A, Y. Dollar display, you can see only once. So you can use display to display any constant values or any one like message one. But if you want to display that whenever there is an execution, whenever there is a change, then use dollar monitor. Is your doubt clear?
Yes, madam.
Yes. here this is the code for the Bahuli multiplier. So you can see this. So the complete half adder full adder instantiation, and then full adder code, half adder code, and then finally IIR filter code. So I have instantiated once the Bahuli multiplier, and then here the D flip flop plus the addition. So if we simulate this, simulation is written as IIR test bench. So you can change this to radix decimal. So first is 2 1, and then this value clock 0 reset 0. So y is 1. So we have seen this. Is when y of 0, 2 into 0 plus 1. So we got 1. Then next 2 into 1 plus 1, which is 3. So the next simulation 2 into 1 plus 1, which is 3. The next simulation 2 into 3, 6 plus 1, 7. So this is the IIR filter code and the simulation results. Then this dollar display, dollar time, and dollar monitor. These are the some of the system task used in the test bench. We have covered in this class signed multiplier, Bahuli multiplier, IIR filter design, and these 3 keywords: dollar display, dollar time, dollar monitor. Any doubts in this? Any doubts? Or I will copy it separately. This is the code.
Madam, I have one doubt, madam.
Yes, yes, yes.
The range, can you explain this? The range of 4-bit signed point, normalized sign to complement number.
Yes. Range for the fixed point sign numbers.
4-bit fixed point, normalized sign to complement number. Range of.
Yes, yes. Sign to complement, and this is in fixed point representation. If we say 4-bit, then it will be A3, A2, A1, A0. Correct? So if we say maximum, okay, if we start with the negative value, This is the possible, so it will be all will be 1. So this will be equivalent to minus 1. And then if you see positive number, maximum value, it will be 0 and all the values will be 1. In negative values, all the values are 0. Because we want the minimum negative value and then maximum positive value. So this will be 0 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 plus 1 into 2 to the power minus 3, which is 1 by 2 plus 1 by 4 plus 1 by 8, which is 7 by 8. So this is like 1 minus 1 by 8. It will get 1 minus this one, we represent, it will be 2 raised to the power 3, which is 4 bit minus 1 and negatives because it is 1 by. So this will be 1 minus 2 to the power minus w minus 1. This will be the max value. For the minimum value, I will cover this now. This is the maximum value. So for the negative, the minimum value, sign bit is 1 for negative and minimum value, so all zeros. So this will be minus 1. Here 0, so we didn't consider the sign. Then it's the minus 83. So minus 0 plus the other terms are 0. So this is minus 1. So the range is from 1 minus 1 to 1 minus 2 to the power minus w minus 1. This w is the number of bits. So for 4 bit is minus 1, 1 minus 2 to the power minus 4 minus 1 is 3. So you can see it will be minus 1, 1 minus this is 1 by 8. Clear? Any doubts?
Okay.
Ma'am, that maximum range 1 minus 1 by 8, can we put it as 7 by 8?
Yes, we can put as 7 by 8, but to get as a formula, we need like general formula.
No. Okay, okay. So one option is there in that question, so like maximum range is 7 by 8 or anything else. So can we put it selected as 7 by 8?
This value is also given 1 minus 2 to the power minus.
No, simply 7 by 8 they have given maximum range.
Yes, you can use. For
Put
generalization
okay,
only, we have used it as 1
okay,
minus 2
okay,
by 8
okay,
and this
okay,
is
ma'am. Okay, 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 okay.
from the assignment 7. We will take one question. Any other doubts?
Madam, this question I understood, madam.
You got it?
Please go to 7 and 8. Question assignment 7, 7 and 8 questions.
7 and 8.
Um,
In this is also pure combinational block, I think so. Yes. Yes. LEG at 85 nanosecond.
If time permits, explain the entire question, madam.
Think
If time permits.
maybe you can, if you simulate it, you will. This TV comparator. The scale is in picosecond. If I resimulate it, I can. Okay. So 85 nanosecond. This will be the value. Seventh question. LEG 010. LEG 010. So if you see the code, 85. Think output of this comparator is LEG. Okay, maybe less than, equal to, greater than. It is comparing A and B inputs. So two inputs. So at this time interval, 85, which is 0, 20, 40. At the 0, 20 till it becomes 40, this will be the value. I want to write this code. This code at 0, A will be 0. Sorry, A will be 1, B will be 0. Then it will become 20. This will be the value. Again, it will go inside this. So from 21 till 40, you can say A is 2, B is 1. From 41 till 60, A equal to 3, B equal to 1. This is what it is following. You can add all the waves. So that is AB I wanted. Yes. So till 19 nanosecond, A is 0, B is 1. Then A is 1, B is 2. Then A is 2, B is 3. So it is executing this for loop. If I execute this for loop, then you can say when from 0, here there is a delay of 20, I think so, correct? Yes. So till this time, A is 0, B is 1. So this will be inside this from 0 to 20. Again at 20 you will see a change. So till 19, at 20 you will see a change. It will be inside this loop. And then this time scale will be incremented to 40. Again at 40 there will be a change. A will be 1, B will be 2. Again at 40 time scale, A will be changed to 2, B will be changed to 3, and time scale will be incremented to 60. At 60 again it will enter this loop. So it will be A equal to 3, B equal to 4. Then after that loop will be reset to 0. So again it will be from 0, and now 1 1 2 2 3 3. The second for loop, which is this for loop. A equal to I, B equal to I. So this after this for loop is completed, A is I plus 1, B is I. So you can say that for loop is executed. So this one at 20 itself it will be here. So this has to be before 20, sometime before 20. Till 40 it will be here. At 40 you will see this change. You will be incremented to 60, but at 60 itself you will see the other change. So sometime before this, say 19 point something, based on the precision of the time scale. So now the given in the question is 85 nanosecond, which is somewhere here. I think so. So it is equal because both are 0 0. Now is it clear?
I have not understood.
Actually, this for loop is getting executed. First, this for loop is getting executed. From 0,
Explain the for loop clearly, madam.
huh?
Once again, if you don't mind.
Yes, yes. This, there are actually 3 for loops. So this 3 will be executed after 1 by 1. So if I take the first for loop, so this first for loop, so from 0 time unit A will be I, so A will be 0, B will be 1. And time scale will be incremented to 20. So after 20, this I is also I plus 1. Again, it will start from this loop. So at that 20 instant, you will see the value of I and B. Again, incremented by 20. And after this, again, it will enter the loop. So it will be A equal to 2, B equal to 3. It will be A equal to 3, B equal to 4. At 80, it will enter this, but I is now greater than 4. So this loop will complete the execution here. So at 80, the next loop execution will start, which is again from A equal to 0, B equal to 0. So for that for loop, like, both A and B are equal to I values. So again, then 80, 90, 100 after 20 delay. Again, both are equal to I. So A equal to 1, B is equal to. Again, after 20 delay, A is equal to 2, B is equal to 2. Again, after 20, A equal to 3, B equal to 4. Now, I will be 4. It will come out of this loop. At 60, it will enter into the third for loop. My third for loop is so third for loop. A is equal to I plus 1. So at 0, it will be 1 and this will be 0. Again, I will be incremented, this time unit will be incremented with a delay of 20. A will be 1 plus 1, I plus 1, 2, B will be 1 at 20, so 200. A will be 3, B will be 2. At 220, A will be 4, B will be 3. After this loop will be completed. So in the simulation also, you can see the same thing. It is 0, 1, 1, 2, here 2, 3. Again, this point, it is getting 0, 0. And here you can see 3 plus 1, it is 4, but only 2 bits are there, so it is 0, 0 again here. At this point again, both the another loop is starting. Till here A equal to I, B equal to I. From here 160, so somewhere this point 160 till 180, it is 1, 2. 160 to 180, it is 1. This point A is at 180, A is 2, B is 1. At 180, A is 2, B is 1. Now is it clear? This for loop execution alone.
Yes, madam.
Yes, so you can see the same thing, and then so here at 180 this is changing. Sometime before the 180 will be the previous value retaining. Any doubts?
time scale 1 nanosecond by 1 picosecond. What does it mean, madam?
They have given 1 nanosecond, so every unit will be indicating as 1 nanosecond. So it is after 20 nanosecond, after 40 nanosecond. So you can see in the execution, like this is 0 after 20 nanosecond, again after 40 nanosecond, and then the precision is 1 picosecond, I think so. Yes, it's 1 picosecond. So every 1 picosecond it can detect. Then
Madam, come again. What does precision
like
tell
every
me
1
about?
picosecond it can detect. That's why you are able to see every 1 picosecond in this one waveform. Changes at every 1 picosecond can be detected. So if you give 1 picosecond by 1 picosecond, then you can detect 1 pico, but you cannot detect 1.5 picosecond.
Okay.
Ma'am, previous year question, assignment 8, 8, fourth question, repeat, ma'am.
Fourth question, this one.
Yeah, ma'am. Ma'am, this is a 2 power minus 2,
Yes, yes.
2 power minus 1, 2 power 0 that come. Minus a plus a means
Plus a once you are saying a into 2 to the power plus 1. Is your question like a 2 to the power plus 1?
ma'am, a plus a
Plus a, this is the notation. So if you extend,
minus a, minus a means a power minus 1. A 2 power minus 1.
a 2 power minus 1. Yes, it will be 1
Minus a means
this will be the shifting, one shifting. So you will have a0, a1, a2, a3. So one is shifting, a1, a2.
minus a means a to power minus 1. It's correct?
Minus a 2 to the power minus 1.
No, minus a means
Okay, if we are extending, the a3 bit will be the sign bit. If it is negative number, then a3 will be 1, so 1 will be extended. If it is a positive number, then a3 will be 0, so 0 will be extended. So for positive number, there won't be any change. This is
ma'am,
the notation. So a3 extension is for both positive and negative.
minus a. It will give the question. Means what? Do solve.
Madam, I think the question is if a 4-bit fixed point normalization signed to 2's complement representation of A is A3 dot A2 A1 A0, then minus A is. That is the thing she is asking, I think.
Okay, minus a. That will be the 2's complement form. Minus a you can represent by sign magnitude or 1's complement or 2's complement. something like this number, you will do the complement and then add 1. If this can be represented in sign, magnitude, 1's complement or 2's complement. So, is this your question?
Then what will be the answer, madam?
So, the sign bit will be fixed, so we won't change. This will be complement. This will be again complement. A0 will be complement. This term alone you have to perform one addition separately with 1. If you are taking 2's complement.
Ma'am, then which bit will be shifted to the right side? Means after the decimal point towards the right.
Minus a you need not shift. If you want to multiply with any 2 to the power of negative number, then you have to shift to the right.
Okay.
For minus 1, 2's complement or 1's complement. For multiplying with 2 to the power minus 1 only, right shift. For multiplying with plus 1, left shift. For minus a is like minus 1 multiplication, so no shift.
Okay, ma'am, got it.
Yes. Any other doubts?
Madam, is the session completed?
One more summary section is there.
Okay.
No, I don't have idea. Like, I think there is a summary section, or I don't know. You received
When
any?
it will be there, madam?
No, you received any mail?
No, madam, I have not received any.
Then I think maybe the section is completed. If there is any
Can
section,
you give any suggestion,
mail.
madam?
If there is any summary
Can
section,
you give any suggestion?
yes. Suggestion. If you have any doubts, like we can ask. Maybe we can discuss.
Ma'am, then after these sessions, if you have any other doubts, how can we contact? Is that possible?
Maybe if you can raise in the forum, or you can mail to me.
Okay, ma'am.
Mail ID.
Madam, you will answer in the discussion forum.
Yes. Or you can mail to me.
Mm.
I have shared the mail ID.
Madam, please refer some textbooks, madam.
Test books. There are books separately you can refer for Verilog, which implements digital implementation books. Currently, I don't remember the author name. And Samer Palikar you can refer for Verilog syntax and everything. And IEEE website also you can get the particular version syntax you can find.
Ma'am, for this multipliers and all, which book we can refer, ma'am? For all types of multipliers, signed multipliers, like.
I don't remember the book, but I think it's taken from. They have given the book's name.
given the book's name.